Good morning, everyone. So, thanks for joining in on this Saturday morning. Today is the 63rd episode of Gyaniki Tech Talks, and we are joined today by Mr. Vilas Chinchankaron. Vilas sir comes with a very rich experience of 37 years, leading the engine performance development and emissions optimization for natural gas and diesel engines. He has uh, led most of his career at Cummins India Limited, leading the alternate fuel and CNG emissions and engine development team. Specializing in the alternate fuel, which has now become a talk of the town with the increase in the discussion of hydrogen as a fuel on the IC engine, and also the use of hydrogen along with fuel cell to come up with what is the fuel cell electric vehicle. So Vilas comes with a rich background in understanding the use of hydrogen as a fuel, and today we are here to discuss on the same with him. Vilas sir has been representing in technical forums at different places, including Cummins US, IIT organizations, IISC, VJTI Mumbai, covering these topics related to alternate fuels and hydrogen as a fuel. He has a global work exposure across continents, Europe, Asia, and US. And presently, he's working as a technical consultant in this domain. Sir is also leading training and skilling in the area of alternate fuel technology. And apart from the session we'll hear today in terms of the base of the technology, there is also opportunity of engaging on longer term training programs on the topic with Vilas. So again, a very rich experience of close to 40 years and coming with a lot of insights. We have Vilas sir with us today. So over to you, sir.
Yeah. So very good morning, and uh, thank you, uh, Shekhar, for introducing me and a nice word. I welcome all the participants for this hydrogen mobility solutions tech talk organized by Gyaniki, and I thank uh, Gyaniki for giving me this opportunity to give uh, this particular technical talk and share my views on this particular subject. The first, I will like to acknowledge Gyaniki Tech Talks uh, for organizing this particular seminar, as well as I would like to thank various technical experts, various company press and media releases, and video contents from where I have taken the references and I have enhanced this presentation. This has helped to enhance this presentation. Of course, as Shekhar rightly said, this hydrogen is a very important subject, and it is coming in various platforms, and lot of work has been done as well as being done across the globe. So capturing all these things in 1 hour is really a challenge. I will try to do that, but of course it needs in detailing lot of time, and certainly uh, you will appreciate that. Here we will be going through the contents like drivers for use of hydrogen, hydrogen technology overview. Then we will going with a fuel cell technology overview, internal combustion engine technology, gas production methods, and we will see what are the colors of hydrogen, gas properties and impacts, reference to ICE and solution, internal combustion engine, that is ICE architecture overview as reference to hydrogen, ICE vehicle overview, and after that we will have question and answer session. Here, first, we will talk about the drivers for use of hydrogen. So, what is we are talking about these hydrogens? Here we know that if we talk about hydrogen, why the discussion is coming about hydrogen now? Uh, Environmental impacts and the environmental regulations, they are compelling us to go for hydrogen. Lot of government initiatives in line with the global initiatives and the requirements, they are talking about hydrogen. Hydrogen being a zero carbon fuel, so it is a right answer for overcoming CO2. It is also a renewable source of energy, and it can provide energy sustainability. So these are typically summarized drivers for the use of hydrogen. Now, uh, here we can see over this particular slide, everybody know that CO2 emissions are increasing over the time as through the industrialization, the use of fossil fuels has increased, which of course carbon-rich fuels that has led to increase of CO2 emissions. And we know that in 1950s, the US and European countries were the biggest emitters. Between 1950 and 1980, China's annual emissions grew by nearly 1,800%. And now, if we consider the today's case, China, the US, and India alone account for more than half of the world's CO2 emissions. So CO2 emissions are increasing as we know. CO2 emissions are leading to global warming. And as the world organizations are discussing this phenomenon, and in COP21, that is a Paris Protocol, it was discussed and decided that we need to control the rise in global average surface air temperature less than 1.5 degrees centigrade as compared to the pre-industry level, that is 1850-1900. So the below graph indicates on the y-axis the global average temperature rise, and on the x-axis the years. Now, if we find this is the actual graph, and it is estimated that it will reach here 1.5. However, the global average surface air temperature in 2024 exceeded 1.5 degrees centigrade above pre-industrial level, and that is as per the World Meteorology Organization. So this is very alarming. And now there is an urgency for decarbonization in a more advanced way, or I would say more rapid way. The global warming causes environmental impacts. And now every day we are seeing that as a challenge. For example, heat waves across the world, they are coming, and they are coming in severe everywhere, not here in Asia in US, in Europe, everywhere. And due to that casualties, due to the extreme weather conditions, which we have also experienced, cyclones are coming in more frequency, more numbers, and they are causing havoc. Excessive unseasonal rains, floods are coming. Adverse impact on farm produce and food availability. That is also happening. And rise in sea levels is causing coastal areas getting submerged. So if we see all these environmental impacts, certainly we need to control the global warming. And as we discussed, there has been a global urgency to mitigate this risk. And above changes are causing mainly due to the extensive use of carbon-rich fossil fuels over the years after the start of industrialization. And now there is a strategy to develop decarbonization technologies for biodiesel, natural gas, renewable natural gas, and hydrogen. Uh, the basic requirement is here decarbonize. And can that happen immediately? No, there is no immediate solution. And here there is no light switch event that just you go change over. So I would say that the wise approach would be to use the technologies which are already available and which will reduce the impact of CO2 emissions, reduce CO2 emissions, and the goal is net zero. So that should be the our way of going towards decarbonization. On the next slide, if we see, uh, there are zero CO2 technologies. Here, we see a green part that is battery electric vehicles. Now, battery electric vehicles, that is BEV, which is called, they are already well familiar in a two-wheeler section as well as passenger car section. That can take care of urban areas, and that I would say that is a good start. And also they can take up to some regional thing, but of course they are having some uh, I would say anxieties. For example, what is the battery cost? Then what is the charging time? Can I get the charging? What is the range? And what will be the battery replacement cost when I will need to replace the batteries? And a lot of things. Of course, that is a good start. And if we talk about long haul, means for example, dump trucks or maybe a long distance buses, trucks carrying cargoes, heavy duty trucks, commercial vehicles, and even say trains. Then we talk about these ships, etc. So, what is the solution for that? Uh, we see hydrogen technologies as probably a good answer for those sectors, long haul, or we can say long haul operation. So those are considered, those are being considered as our future technologies. And now, world over, everywhere, the more thrust is given on you improving battery technologies as well as seeing for the zero emissions and impact to the global total cycle. Hydrogen would be a better option. Now, if we see from the India national government perspective, because India is also part to the world organizations, and India has prepared national green hydrogen mission for decarbonizing India and achieving net zero. In short, the vision says that become energy independent by 2047 and achieve net zero by 2070. So that is the real goal. And there are mission statements how it can be done, which is explained here. I will not go into details of that considering our time today, but this is a very backbone of our hydrogen journey in India. Now we talked about the requirement or the drivers about hydrogen, and now we know that the government is also considering that as a major future technology for transportation sector. Uh, Now we will talk about hydrogen technologies overview. Here, you may be aware that mainly the two technologies at present are being discussed in a hydrogen arena. That is, one is a hydrogen ICE, that is hydrogen internal combustion engine, and another is a hydrogen fuel cell. Those are the two technologies parallelly being developed, parallelly being evaluated, and of course, world over, there are discussions going on which way to go. And of course, each technology has advantages as well as disadvantages, and need to consider going forward the optimum way, which is right for the net zero. Because the final goal is we need to achieve net zero emissions. Now, if we look at this slide, hydrogen ICE, here we can use 100% hydrogen instead of any fuel, for example, diesel, natural gas, etc. Here we can use 100% hydrogen. It is not a dual fuel, 100% hydrogen. Here we can take care of a 99% tailpipe CO2 reduction. And I will explain why I'm saying 99. 75% tailpipe NOx reductions reference parent diesel engine. The main advantage here is lowest initial cost and the maintenance cost. High technology readiness is already there. And the one important thing is that if we consider this is the place where the engine is placed, here the hydrogen engine can be installed, remove the existing diesel engine platform or this natural gas engine platform, and this can be inserted very easily. So we can use the same driveline components. So that's the beauty about this easy adaptability to the existing platforms. Vice versa, if we consider hydrogen fuel cell, of course, the technology is totally different. And here also we can use 100% hydrogen. Here we can get 100% tailpipe CO2 reduction, 100% tailpipe NOx reduction. Here, higher initial cost and maintenance cost. Because here, the cost of having different drivetrain components, then different, say, technology. So the costs are high. The battery charging time and the replacement cost, the prototype demonstration stage vehicles, and complex transmission and chassis integration. So those are some of the quick overview points on the hydrogen engine and hydrogen fuel cell technology. After looking very briefly about this overview, now what I will like to go, uh, having a quick technology review for hydrogen fuel cell. Uh, but my main intention of this is today's intention is to go with a hydrogen ICE, internal combustion engine technology overview. So that is the purpose. Now, in this, if you see this hydrogen fuel cell car, Toyota has been very pioneer in this. And here on the vehicle, you can see the hydrogen tanks installed, fuel tanks. Then we can have a fuel filler similar to uh, this. Then here, fuel cell stack. What is fuel cell? We will discuss in a minute. And then there is an electric traction motor, and there is a DC AC converter and thermal uh, systems. Now, it is in quick, it is a battery electric vehicle where the charging system is on board. So with the use of hydrogen. So that is the, in a quick, uh, I can say, this is FCV is nothing but a BEV having its fuel cell means charging system on board. Now we will look at this hydrogen fuel cell. Now in hydrogen fuel cell, typically is a very quickly can be similar to any cell. Here we get hydrogen from the storage tank in an anode chamber, and we get oxygen from the air in cathode chamber. There is a platinum catalyst used, PEM, proton exchange membrane is there, and there is an electrolyte, KOH electrolyte is there. Here what happens, due to this platinum catalyst, the H ions are separated and they are with the cell, they are mixing with the oxygen and they form H2O. And the electrons released, they go to the charging system. So in short, this is very top level, I would say, hydrogen fuel cell. Now, here in details, the working has been given, but I will not go in more details here. Uh, Now, we will quickly see what are the applications for the hydrogen fuel cell technology. Uh, and Cummins, also a leader in this particular technology, is supplying heavy-duty hydrogen fuel cell systems to power zero-emission buses and passenger trains. So the development as well as prototype development is over already. The pilot testing has been completed and actual applications are in place. NTPC, that is National Thermal Power Corporation, is setting up a hydrogen fueling station, solar plant, and providing 5 fuel cell buses for operation on intracity routes in Leh. That is typically a hydrogen uh, fuel cell vehicle, and which is, of course, with the help of Ashok Leyland. Now, world over, in Australia also, the hydrogen fuel cell buses are being supplied from the Photon, China. We can see hydrogen fuel cell technology is also being used in Saudi Arabia for railways. And to just mention, in very similarity, Indian railways, they are going to commission their first hydrogen fuel cell powered train by March end. So in India also, we are having the similar pilot projects going on. Now here you can see on the marine applications also, the China's first hydrogen fuel cell powered boat completed its maiden voyage. And I mean, the idea is that many institutions are trying various applications to by using hydrogen fuel cells to replace the existing power packs. So that ends our quick overview on the hydrogen fuel cell. Now, we will talk about hydrogen ICE technology overview. Now, this is typically IC engine, and we understand the drivers for hydrogen ICE technology. Why? Because we discussed the drivers for hydrogen. But if we see the legislation here, the diesel internal combustion engine is banned in certain areas. Then there are time to wheel legislations are coming up, and it becomes very difficult to meet those regulations. Another thing is, as we discussed, rapid decarbonization. The need for rapid decarbonization, and hydrogen has no carbon in it, in so that we can go for a faster decarbonization. So that's the way. And of course, we will talk about green, pink hydrogen, etc. Then another thing is job security. Here, with the use of hydrogen in IC engines, that promises to extend the life of internal combustion engines, the existing technology with the added advanced technology, and that helps from the job security. Then, of course, geopolitical security, because hydrogen can be generated uh, indigenously. We may not be required to depend on external sources. Supply chain, domestic supply chain can be then TCO, total cost of operation and upfront cost, certainly is a very important from the customer perspective. Materials and infrastructure. For example, in case of ICE, at present, no limitation. In FCB, we require batteries, precious metals, platinum, lithium, cobalt, etc. Also, the electrical grid limits are there, and we need to have a mining ramp up. So those are the drivers for going forward with the internal combustion engine technology, enhancing the life of the existing power solutions. Now, here we see the hydrogen internal combustion engine. In many leading global companies have chosen path for using IC engine technology over hydrogen FCV, considering following points: extension of existing diesel, gasoline, natural gas architecture, fewer changes related to cylinder head, air handling, and ignition system, lesser changes in chassis power transmission, faster path for product development and achieving decarbonization, lesser hydrogen fuel refilling time versus longer charging time required for batteries, lesser maintenance cost, overall less disturbance to environment, mining, and energy requirement as may be required for mining specialty materials needed for battery, higher cost of FCV versus ICE, and complexities involved in FCV. Now we see hydrogen ICE technology companies. Here, if we see Cummins, Tata Motors, Ashok Leyland, Reliance, Bharat Benz, I'm talking companies in India, which have applications in commercial vehicle and buses. JCB, which is a very dominant name in earth moving equipments, and they are also working on hydrogen. Then Ford, Toyota, Tesla, and Hyundai, they are also working on hydrogen powered car technology. So, people, even Tesla is mainly viewed as a BEV company, but they are also working on parallel solution using hydrogen. Now, we can see on this slide uh, Tata Prima H55S hydrogen ICE powered truck. And this basically truck is powered by Cummins 6.7 liter hydrogen engine with 290 HP and 1200 Newton meters torque. And range is about 350 to 500 kilometers. Of course, it depends upon the cascade of hydrogen cylinders which we use. And the applications are basically cement, coal, fly ash, bulkers, steel, coil movement, bulk cargo, construction, aggregates, haulage, and distribution. So that's basically for heavy duty commercial vehicle applications. Now, you must have seen this newspaper uh, or maybe on our media that Tata Motors have recently started field trials for hydrogen internal combustion engines and vehicles powered with FCV. They are trying both the technologies, evaluating on the road its all the parameters, and certainly they will come up with the recommended path going forward. And the news item suggests that 16 trucks to drive across key freight corridors in India, paving the way for a net zero emissions future. And here, Honorable Minister Nitin Gadkari uh, inaugurated this particular test trials for TML. Now, coming to earth moving equipment side. JCB is very pioneer company, and there you can see they have started using hydrogen. They have completed the initial trials, I would say. The JCB, they had a good investment into H2 IC technology, and here the various steps they have taken on their four-cylinder hydrogen engine. And here the recent media uh, disclosure is that in 2025, they have completed all the regulatory certifications at 11 European agencies in Europe. So JCB has already completed the development work. They have completed, I would say, the emissions certifications work as per the EC regulations for the Europe. On the tractor side, the TAFE has announced its entry into European market with hydrogen uh, engine as well as along with an electric tractor and a concept tractor. So TAFE, uh, a tractor company, is also working on these future mobility solutions with hydrogen. Ashok Leyland has demonstrated and exhibited their prototype trucks in the exhibition which was held in Delhi, Bharat Mobility Exhibition held in Delhi. We discussed about the hydrogen ICE engine, had an overview, and now let's consider how the hydrogen gas is produced. Because, okay, we discussed about the applications. Now let us understand how the gas is produced. Now, if we talk about this hydrogen, here we see the colors of hydrogen. It doesn't mean that the hydrogen gas has a color, but depending upon the method of production, that is termed in a different color. For example, for generation of hydrogen, if coal or lignite gasification is used, it is called as a black or brown hydrogen. If natural gas is used with steam methane reforming, then it is called as a gray hydrogen. Then if we use natural gas with steam methane reforming and carbon capture, then it is called as a blue hydrogen. And if we use a nuclear energy and use a electrolysis, then it is called as a pink or a purple uh, hydrogen. And if we use renewable energy, such as windmills, or we use a completely renewable energy, then and use electrolyzers, then it is called as a green hydrogen. And of course, if you see these methods of production and considering the life cycle, the more desired option is going with a green hydrogen or a purple or pink hydrogen. But uh, for a road to going there, maybe we will have to use some other options here. But for net zero solutions, we need to go with a green hydrogen or a pink or a purple hydrogen. Now, in this slide, typically, as we discussed, hydrogen, brown hydrogen, it is from the coal gasification. The gray, it is from this, and if we talk about the blue hydrogen, it is a steam methane reformation and carbon capture. And the green is typically from this complete renewable source of energy. And we can say that is most desired option to be used in ice. The another thing is that as we talk about the other production methods, there has been a recent discovery of natural hydrogen reserves at many sites, namely Nebraska, USA, France, and Australia. So we have seen these news coverages are coming up. And recently, France has recently discovered the large reserves of these natural hydrogen. And the term being considered on this is a white hydrogen, but that, I mean, it's need to be finalized. And the impact of its discovery, how it can be taken out, how it can be handled, etc. So a lot of discussions are going on this. Now, as we know about these methods of production of hydrogen, now let us talk or understand the hydrogen gas properties, because this is really very important from the perspective of use of hydrogen in internal combustion engine. As we all know from our periodic table, hydrogen is say atomic number 1, symbol is H, etc. So uh, I will go to the next slide. And this is, I think this is very important slide, because the next slides, those are based on these properties and how the hydrogen use has advantages, and has we need to do what are the solutions on the challenges. So it answers all the things. So if we see on the chemical and physical properties of hydrogen, here carbon content, if we consider hydrogen, CNG, gasoline, and diesel for the comparison, carbon content in hydrogen, it is zero. Very, very important thing, because for achieving or for reducing CO2 emissions, this is very, very important for net zero. But CNG has 75% mass of C, gasoline 84, diesel 86. Then if we consider net heating value, that is a calorific value, mz per kg on a wet basis, hydrogen is having 119.7, CNG 45.8, and others. So it is well seen that hydrogen is having very good heating value per kg basis. I would say about 3 times the higher than the CNG on a mass basis. Now, if we consider density, it's in other term, that is the hydrogen has the least density, that is 0.089, and others are having heavier density, molecular weight. Now, this is very important. The sixth is very important. Atto ignition temperature. Atto ignition temperature for the hydrogen is 858 degree Kelvin. For natural gas, it is 813, gasoline 623, and diesel 523, like this way. So this is very important auto ignition temperature characteristic, which has an effect on combustion and design of or selection of the other parameters. Another thing is minimum ignition energy in air, millijoule. Hydrogen requires smallest energy, that is 0.02 millijoules. But CNG requires maybe about 10 times or more than 10 times of that. Then stoichiometric air-to-fuel ratio mass. We will talk about what is meant by stoichiometric at a later slide. But on hydrogen, it is 34.3. And for natural gas, it is 17.2 and 14.7 and further 14.5. So this means that as compared to the natural gas, hydrogen requires 2 times more air by mass. So this is a very important thing. Then the flame quenching distance, that is hydrogen has the lowest flame quenching distance, that is 0.64. And for natural gas and gasoline, it is 2.1 and 2. And we can see the consequences of that in later stages. Laminar flame speed is the highest for hydrogen, that is 1.85. For CNG, it is 0.38 and others. Diffusion coefficient in air for hydrogen is 8.5 into 10 raised to minus 6, while for CNG is 1.9 into 10 raised to minus 6. Flammability limits in air. Hydrogen has a very wide flammability limits, that is 4 to 76, while natural gas is having 5.3 to 15 and others. And adiabatic flame temperature for hydrogen is a 2480 degree Kelvin, the highest in the lot. And natural gas is 22142580 and diesel 2300. So this is a very, I would say, compact comparison of various properties, which now we will talk in the coming slides. Now, when we talk about the flammability limits and air-fuel ratio, now here you will see on diesel, you have a very narrow range. Then on gasoline also, we have very narrow range. Methane also we have 5.3% to 15% in air. But hydrogen, we have 4% to 75%. So this is very important. And with the hydrogen, it is easier to start lean mixture with the hydrogen, because lean means when you have excess air, still you can be able to start the mixture because of this wider flammability limits of hydrogen. Then ignition temperature, the self-ignition temperature for the hydrogen is the highest. And here, with that, we can have higher compression ratio, of course, on a lean burn engines, and hence we can be able to achieve higher thermal efficiency. And this can also resist knock. Ignition energy. Hydrogen requires the least of ignition energy. And due to that, it is easy to ignite lean mixture, because typically when we talk about hydrogen from the safety point, we need to run the engine with a lean combustion mixtures. And so that is, of course, we need to take care of hotspots, misfire, which is also because with us, it requires very small amount of ignition energy. So we need to be very, very having a good analysis, ALD analysis for understanding the combustion chamber design and the flow dynamics. Now we have briefly looked about these hydrogen gas properties, and now let us look at now let us look at the quickly about its impact. Now we know it's a zero carbon fuel, burns cleaner and does zero CO2. So no carbon emissions, higher calorific value. So that due to that, we can get with a lesser mass required for the same power. Higher stoic air to fuel ratio mass. With that, we have to have a higher mass of air is required, needs to run leaner combustion leading to low NOx emissions and higher fuel economy. Higher auto ignition temperature. We can use higher compression ratio piston that will lead to higher efficiency and fuel economy. Low ignition energy. We have discussed about that. Higher flame speed due to that can be controlled by running lean mixtures and helps for better fuel economy. Then smaller flame quenching distance from cylinder wall, 0.64 mm, can cause backfire by charge leaking through cylinder head, wall, inserts leakage path. And for that purpose, we need to have the proper selection of cylinder head, cylinder walls, and cylinder wall inserts. At the same time, we need to have a combustion analysis, CFD, done for this so as to avoid the backfires. High diffusivity, faster diffusion as compared with gasoline. Natural gas leads to faster uniform mixture, better combustion leading to higher efficiency. It reduces the danger from a leak. Now, if we talk about the combustion equation for hydrogen, it's very easy. And here we find it is an exothermic reaction, and the products of combustion are only water. No CO2 or PM emissions. Very, very important from the net zero application. So zero CO2 PM emissions. And here, of course, due to this combustion, we can get NOx. However, by running this engine with a lean burn combustion, and we will talk about the lean burn combustion, we can reduce the NOx. And if at all required to meet the regulations, may need after treatment for NOx. This is a very, I would like to define what is lambda for the sake who are not coming from the internal combustion engine background. Here, we know that every fuel needs a typically air for complete burning, and the ratio of air required for a unit mass of fuel is called as a stoic. And if we consider lambda, it is the actual air mass, fuel mass, actual divided by the required by the stoic. So that is called as a lambda. For example, for a hydrogen gas case, if actual air to fuel ratio is 60 by mass, whereas the stoichiometric air to fuel ratio is 34.3 by mass, the lambda is 1.74. The mixture is lean. When lambda is less than 1, mixture is rich. When lambda is equal to 1, mixture is stoic. And when lambda is greater than 1, mixture is lean. Now, just to quickly understand, here on the y-axis, it is lambda. Please understand, this is a graph I have taken from the natural gas combustion. Here, lambda is equal to 1. We call this is a stoic. Lambda less than 1, we called as a rich mixture. Lambda greater than 1, we called lean burn. Now, if we consider a NOx profile, NOx is the highest or near highest at the stoichiometric range. But as we move towards leaner mixture, as we have excess air to fuel ratio, the NOx starts decreasing rapidly. In case of lean burn hydrogen operation, we can see at 1.2, the NOx is maximum. But if we run this at 2.2 lambda, the NOx is 14 ppm or 0.07 grams per kilowatt hour at lambda. So, in short, uh, with a combustion with hydrogen, we only get water vapor. NOx is there, but can be controlled with a lean burn combustion. Uh, Now we will talk about quickly about ICE architecture consideration. Here we talked that uh, we have a diesel engine, we also have a natural gas engine, and we want to have a commonality of parts. So we can use or develop hydrogen engine based on various common parts which are used in diesel, natural gas, and hydrogen. Only the parts which are required reference to the combustion and reference to the air handling, reference to the fuel handling, they need to be changed. So that is how we can use most of the common parts in this transition of technologies. Now, in case of a hydrogen internal combustion engine, if we compare diesel, hydrogen, and natural gas engine, the base engine is same. Installation parts, mounting parts are same. Cylinder head for hydrogen and natural gas can be similar. There may be some minor changes. Ignition system, hydrogen and natural gas similar, minor changes. Engine control units and software control units can be used same, but software calibration needs change. Fuel system, of course, hydrogen is different. Air handling system, hydrogen is different. After treatment system, similarities between diesel and hydrogen. Challenges working with hydrogen. Now here we know that we have to have twice the higher stoic A by, say lambda is equal to 2. So we need air handling system need to be optimized. So this is achieved by specialized design of air handling, turbocharger, intake manifold, valves, and valve trains. Hydrogen fuel supplied to engine cylinder. This is achieved by using GDI, gas direct in cylinder injection, because to achieve high power density efficiency compared to port fuel and avoid possibility of intake manifold overpressure event, IMO. Ignition system. Here we need to have an ignition system which is coil over sparkler, essentially with a colder range of sparklers are used. Also, specialized cylinder head cooling passages are designed so as to reduce the possibility of in-cylinder hotspots to avoid pre-ignition or and not. Now, here different combustion chambers are there, but here on GDI, we use high pressure gaseous hydrogen intake gas direct injection system in case of hydrogen. Now, exhaust after treatment, we discussed on that. Well, another thing, crankcase blow-by hydrogen and ventilation. Improved piston rings designed to reduce hydrogen mix blow-by, ensure positive crankcase ventilation. Lubrication. Improved lubricant life suitable for operation with hydrogen gas is needed. Overall engine safety. Considering hydrogen operation, overall safety needs to be provided by using safety relief valves over crankcase intake manifold with proper ventilation to avoid any thermal events. Then there is one another term, hydrogen embrittlement. The embrittlement is the loss of material's ductility due to a chemical or physical change, leading to crack propagation without appreciable plastic deformation. Here, special materials need to be used, typically for walls, for stainless steel 316/L, etc. And there is a lot of work has been gone on this particular thing. Now, quickly summarizing, considering the time frame, the Mahale has developed special component and combustion system for H2 ICE, typically a combustion process, pistons, ring packages, wall sets, and crankcase ventilation. Those are their areas. Then Lorentz and Woodward, they have come up with direct injector for hydrogen, 30 bar operation pressure, and specialized injection systems which are needed for high pressure direct fuel injection systems. Uh, when considering the overall challenges, now talking about hydrogen and solutions. Availability of green hydrogen. Here, India has set up green hydrogen mission and multiple companies, Reliance, IOC, JSW, Adani, have set up ambitious plans for the manufacturing and distribution of green hydrogen. Needs high pressure cylinders. Here, in case of natural gas, we store gas in 200 bar, but here we need to store gas at 300 bar to 700 bar, considering its density. And we need to use composite fiber cylinders. Accidental hydrogen leakage. As hydrogen is lighter than air and has high diffusivity, hence spreads faster, however, care needs to be taken to avoid presence of any hot sources, as hydrogen requires very low ignition energy and has a wider flammability limits. Accidental backfire needs to avoid cold fuel injection and use GDI. Also, special cylinder valve material needs to be used with proper CFT for in-cylinder design so as to eliminate possibility of backfiring. Highly inflammable, extensive R&D to establish design standards for the storage, transfer, and end use of hydrogen. Arresting pressure buildup in the crankcase. We discussed positive crankcase ventilation and provision of pressure relief valves. So overall, there are challenges, and of course, the mitigation plans are being worked out as well as they are being investigated also. Now, this is the last chapter. I will just quickly take a review. Here on hydrogen, we have a fuel delivery system, which is as per the safety standard ISO, TS, ASTM, like that way. And here hydrogen tanks type for carbon fiber and storage pressure 350 bar to 700 bar. And you can see the stack of hydrogen cylinder can be mounted in the back of the cabin. Typically, this is a US cabin and the engine can be seen installed here. Now, in USA, a lot of research work is done uh, funded by the US government along with the consortium. I would say it is a very good collaborative work which has been done and with a Southwest Research Institute. And for example, the engine, fuel injection system, supercharging, boosting, vehicle, then after treatment, hydrogen storage, various expert companies, related companies are involved, and the development is a collaborative development effort is being done there. If we talk about engine efficiency, typically hydrogen reaches 45%, but there is a target to achieve 50% thermal efficiency. Hydrogen economics, if we see on this graph, here if we see the cost of a diesel engine, the cost of a natural gas engine is slightly higher, maybe 20%. But the cost of hydrogen engine would be about 35 to 40% higher than the best diesel at the current rate. But the cost of hydrogen fuel cell will be still higher because of the uh, fuel cell and other engine integration systems required. And if we talk about a battery EV, so the cost will be still higher. So these are typically, I would say, 2027 is a black and yellow is a 2035. So of course, the world over, the efforts are being made to optimize these solutions. Now, in a nutshell, if we see comparison of three technologies: battery electric, fuel cell vehicles, and H2 vehicles. We see that hydrogen internal combustion engine would be a promising solution for mobility solution for the commercial vehicles, as has been seen. But of course, the efforts are being made to evaluate, and the dynamics is changing about the battery technology, battery cost, and the battery range, etc. So, but currently, this is the assessment. On the hydrogen safety, typically we have a completely different chapter as well as for the other sections in detail. But considering the time limit, I'm just giving a very simple diagram. But there is a separate chapter because hydrogen is need to be handled very carefully.
That's all from our side here today at Gyaniki Tech Talks, and hope to see you again on our sessions. Thanks, everyone.
Thank you. Thank you.
Thank you, sir.